Welcome everybody. I'm going to be talking about patterns and idioms, which I've had many times before. Just want to make sure we agree on what's the difference. Patterns are a very general term. They apply at many levels of abstraction. It would be best to always talk about what level of abstraction, like architecture pattern versus design pattern, deployment patterns, and so on. That doesn't mean they are not partially dependent on technology. In architecture, where patterns were born, you have to recognize both the overlap and the difference between patterns suitable when you're designing a log cabin versus a brick building versus something in reinforced concrete. There will be things in common and things different, which is why I keep even the patterns talk usually focused on Python. However, idioms are a much more specific concept, focusing only on artificial languages, which include programming languages. They're essentially a way of expressing a common recurring idea. And exactly because of that, I end up having 2/3 of this talk about idioms. Why? Because the hot patterns today are mostly architectural ones, which have much less technology dependence than, say, design patterns. Why are architectural patterns hot? Because the world is changing very rapidly. Used to be that for many excellent purposes, it made sense to design, deploy, deliver a system running on a certain box, or maybe two boxes with fast connection. It's starting to make no sense whatsoever. We want distributed systems able to run across a huge number and varying number of boxes, and scale stays reliable and everything. So the patterns I'm going to focus on are only the three key architecture patterns that apply more or less whatever language and other details of technology you've chosen to use. Load balancing of various kinds, microservices, and caching. So, diving right into it, load balancing is any case where all work requests or workload go to a central point which fans out to a number of actual servers implementing the service. Of course, as soon as I say a central point, a reliability-focused person says, oh, a bottleneck, this will be the single point of failure for the system. Well, fortunately, when I say system, I don't imply a single server. The load balancer itself can, and for high-scale reliable applications should be, distributed, but it works as a system to distribute incoming load to different servers. Inevitably, all the time in load balancing, you also want to keep an eye on the health of the servers you're going to be fanning out to. Why? Because a core principle of today's architectural patterns is to build extremely reliable distributed system out of not so reliable single servers, single bricks. So the ability to stop putting load on a server which isn't performing well for whatever reason, maybe a memory chip has fried, or maybe it's running a release of the software which has bugs, or whatever. You just don't want to put more user transactions at risk there. You might also want to consider load. There are very many load balancing algorithms. One way or another, since you cannot necessarily predict how much work it will take to satisfy a single task, a single unit, you may end up with one server carrying a heavier load than another. However, the only reliable point to measure that is on the actual server itself. So my recommendation would be to have the health message also encode how loaded the server think it is, so that the load balancer itself doesn't have to maintain state. You'll hear me rave against the state over and over when talking about architectural pattern. That doesn't mean I become an anarchist. I just thinking that stateless has so many advantages if you can possibly get away with it. It means you can if you aren't maintaining state, you can move your load instantaneously to an alternate machine or set of machines. If the core ones are going bad, you can elastically add or contract the number of machines and so on. All things that become so much harder if each machine is keeping its own state. Of course, you typically do need to keep some state. So as we'll see in microservices, the core idea is, well, delegate this to a specialized microservice. Redis is probably the most popular. You need to keep state. You don't like count on it staying in your memory or local disk. You shed it off to Reddit. So in a cloud environment where you are essentially only leasing, renting machines, it's important for the load balancer to be able to look at the loads as reported by all the active servers, make some prediction on how the workload is changing. Is it trending up? Do I have a reliable history whereby around 8 a.m. Work starts increasing and it peaks at 10, and so on, and then request other servers to join the pool available to put work on, with all the due diligence in not having a new server start up and get immediately swamped by being deemed the least loaded and being charged with all the work that's coming in. So all sort of heuristics as well as algorithms that help there. Another bit that I often see lacking in load balancers, especially the pricey dedicated hardware ones, which I don't really like at all, is the ability to distribute traffic unfairly. So for example, decide that particular group of 2 servers only must take 2% of the load, and the remaining 98% goes to the rest of the pool. Why do I care? Well, very often I care because those 2 servers are running the intended new version, next version of the software, of the serving software, and while I have done all my best in testing that thoroughly, I will not feel really secure that the new version is perfectly good and not less reliable or slower or anything until I've seen it serve some live traffic. But if I have, say, at some point a pool of 10, of which 2 are running the new version, I don't want 20% of my users' transactions to be at risk in case the new version has problems. So I very carefully trickle there 1%, then 2%, then 5%, gradually letting them demonstrate that they're perfectly fine. Another idea with traffic splitting in unequal ways is what's called A/B testing. That is one classic example Google did when trying to determine what background color is most effective for search ads. There is no theory that is reliable enough to count on that. So what we did was we tried 1% using pale yellow, 1% using pale pink, 1% using pale blue, and we just measured how many people were clicking on the ads depending on their background color. You'll be surprised, but it makes a difference. So that's how we picked our current color scheme. You may have other figures of metric. From Google's viewpoint, it was high quality, numerous high quality clicks on ads, but others may have other, and A/B testing lets you check. So if you're using Python, there's a couple of popular load balancers that you may want to explore. None of them has all the features I have briefly mentioned. Still, they're very readable code, especially the one that comes with 0MQ. It's actually given as an example. I think it's 80 lines of code. So you can definitely see, understand what it's doing, and why not? Fork it and make your own load balancer, which knows everything about your own application, and be very happy. Oh, I said application, but I should really say service, because the second and almost as important architectural pattern is microservices. Instead of having all the functionality of your modular application divided into libraries, which need intrinsically to run in the same server as everything else, because they communicate via memory, so they need to be sharing memory, split them off as a separate standalone process that communicates on some kind of RPC, remote procedure call. Typically very popular today is HTTP, REST, representational state transfer, and JSON. Better still, do that and then clothe the skeleton of communication into a library which just does all the communication and delegation. Why? Because if tomorrow you move to a different transport mechanism, say HTTP2 with binary frames or a different encapsulation such as Google Protobus instead of JSON or whatever, this can be done in a way that's totally transparent to your application layers. Only the library dressing up the microservice access needs worry. Why do you want microservices? Even though there is, as the penultimate line says, an obvious problem overhead. It takes more, even with a very fast local network, even with a Unix socket, takes more to send 100 bytes than it would be to pass them as a parameter in memory. The core reason is microservices explode the scalability of your application, where previously you were wondering how do I manage to exploit all the cores, and oh my God, there is a global interpreter lock, this will kill me. No, it's completely irrelevant. You can use 10,000 machines as easily as 10, as easily as 1. You start by developing everything on a single machine, on a baby scale of data, and then as your service is incredibly successful and gets millions of users, you just need the money to add more servers to it, which every cloud provider will be very happy to lease to you. As this happens, do consider that nothing says that in a microservice the consumer needs to talk directly to the producer, to the supplier of the service. You can have load balancing inside your application if it grows huge enough. Sometimes I recap mentally the current architecture of Google search, and it's staggering how many caches and internal load balancers we have, because it is such a huge application, of course, with billions of users. As a side effect, microservices were invented with other names, mostly for scalability. Turns out that microservices make your code much easier to maintain, upgrade, and test. Wonderful words. If you're into DevOps at all, these will say, oh yes, how so? Well, upgrade needs only upgrade one layer, like, I don't know, your authentication layer can be upgraded to do it better, to do it faster, to do it more nicely, without affecting all the business logic in your application. And if you're not 100% sure the new one is working, of course you test it very thoroughly in itself. That's why it's easy to test, because you're only testing that one thing, not carrying around all the rest. But then you can use the same techniques you use on outside facing things. You can use canarying, load balancing with with traffic splitting and so on. And similarly for maintenance, suppose an upgrade goes bad, well, you can regress just that service to the previous known good version and be perfectly happy. For some people, it's a big advantage that microservices can intrinsically be multi-language. With Python, I don't see this as an important thing because Python is good for almost everything. So one example I would consider checking out, which does things pretty well as a framework for microservices, except it requires Python-only code on both sides, is Gilliam at GitHub. Let me skip caching because time is really tight. So, idioms. The progress of technology, programming language in particular, although the example on the slide is about machine architecture, swallows idioms. What used to be an idiom becomes incorporated in the language. Python, of course, also swallows, as a great engineer Antoine de Saint-Exupéry, best known for his book The Little Prince, which is a masterpiece of engineering, illustrated in this drawing of a python having swallowed an elephant. Let's take one example. I used to be an advocate of the decorate, sort, and decorate pattern, or idiom if you want to call it, instead of using a comparison function that ends up being called n log n times, which is far too many. You prepare an auxiliary list with a sort key before the actual items. You sort that. The comparison intrinsically goes lexicographically, so the sort key dominates. And then you extract the items again. Nowadays, the key equal construct in just about almost every function does that internally much faster. So people are forgetting the SU, but they're wrong. They should remember, because almost everywhere doesn't mean everywhere. Heap Queue, wonderful module that gives you a heap, also known as priority queue, doesn't do key equals. So you can clothe a heap in a class which essentially adds the key argument in construction and the decoration and undecoration. It doesn't sort, it uses heapify, which is a heap function. It's much faster. Heapify is O of n, while sort, worst case, is O n log n. So this is really much faster. Once upon a time, we only had list, dict, and tuple, and things have changed enormously. We have sets. I imagine all of you use sets regularly, but look at all the other built-ins you probably don't use. Who's used a frozen set? Well, more than I expected. I was the paladin of frozen sets, because sets being mutable, you cannot have a set of sets. And that's just revolted the set theoretician in me. It's like, what do you mean you can't have a set of sets? Isn't that the whole point? Well, you can have a set of frozen sets, almost as good. And besides all the containers, which there's built-ins hardly anybody ever uses, except maybe for, take object, for example. This is the only idiomatic way to use object for other than inheritance. When you instantiate object, you obtain something that doesn't compare equal to anything. That's a perfect sentinel. Sentinel is actually a pattern because in different ways it applies across languages. Essentially, for example, you can have a sentinel as the default value of a parameter. This way you can determine for sure if the parameter was explicitly passed. I'm assuming, of course, the caller isn't reaching into your module and using a private, because starting with underscore, name. More commonly you'll see none, but I could call f of none explicitly, and in this hypothesis I don't want to be confused if something has been passed or nothing has been passed. This is clearly distinguished. Similarly, if you use get on a dict and as a default value you return a sentinel, then you know for sure by examining x later whether the key was there or not. without needing to test explicitly. You can test on the get return. There are other ways to do specialized sentinel. This is, for example, a decorator that gives you a sentinel that gives you a modified predicate which is always satisfied by the sentinel. Why do you care? Well, for example, you put the sentinel at the end of the list and then search for the first item satisfying the predicate, and you know there is one because the sentinel at least will satisfy it. Thanks to all this progress, a lot of idioms have been swallowed. One example, who has used in the last year set default? Wrong, you shouldn't have. There is never any good reason. Why is it a problem? Because, like most languages, Python is eager. When you call setDefault x empty list, that empty list is being built every time, whether it's needed or not. Built, thrown away. Built, thrown away. And they say Python is slow. Python is slow if you use it wrong. Like that. Use a default dict, and the list will be called, the factory list will be called only when needed. So presumably very rarely as data arrive. And then we have whole generations like, let's count how many kind of things there are in a sequence. Used to be that you had to check, actually the in is also a modern construct. You had to do if d dot has underscore key open paren x close paren. Then we added in, and that became the idiom. Then get, giving you a default value if absent, and then default dict, doing that even more smoothly, and finally counter, which does all you could dream of. This goes for IO too, but I really have no time. That counter is essentially a multi-set with a twist. It's a pretty fantastic multi-set that can have a multiplicity that's negative for an item. I don't think there's an exact mathematical model of what does it mean to have an item minus 2 times. But this has the advantage that you can subtract counters and normalize counters, so to discard all the negatives. And this, for example, tells you which items happen more often in a sequence than in another. That's very easy. I pick 2 sequences, which are a phrase in Italian, a phrase in English. I make a counter from one. I show every step, as you see, subtract the other, then do the normalize in x6, and that's all there is. Only those 3 items which are more common in x's, A, L, and T, happen more often in x. All the others happen equal numbers or more often in y's. And I don't think we have, okay, let me skip a few things given the ridiculous times and mention a trap I've seen people fall into order dict. Can you understand why building an order dict from some existing dict is totally useless in any case? Because the sum dict has no order, so the order dict will carefully model and replicate that lack of order, which is completely useless. But it's not obvious that this also happens when you use the elegant keyword idiom to build the order dict. Whether A or B comes first, you may think intuitively, well, is B first and then A? Nope. Doesn't have to be. The B equal 1, A equal 2 is internally mapped into a dictionary. So you have to use the clumsy construct with a specific sequence. Or you don't actually need a sequence, you need the iteration order to be preserved. So you could have used a generator instruction. And I'm just pointing out that instead of building a list and to process, you can generate items on the fly. List comprehensions are very elegant syntax, but the semantics is still they're building a list in memory. Memory is not exactly free. Yes, it's gone down a lot in price, but you still pay something. So the generator is actually a much preferable alternative. And itertools gives you a lot of performance on top of that, and generators have become coroutines. Of course, besides the power of iter-tools, there's plenty of generator, like people want the first item, okay, I think our time is over, but people often don't realize that the built-in next can actually be used to get the first item in the generator, either with an exception if there is none, that is, generator is empty, or with some sentinel or replacement value. And unfortunately, we're out of time because I need to keep 5 minutes for room changes. So thank you very much for the extension, and my apologies for having received so little time.
Thank you.